can you draw PV diagram now of the Carnot cycle? Please, please make a pause and then try to make your PV diagram of the Carnot cycle based on these 4 processes we just discussed. I draw a PV diagram here domain, and let's try to draw 1, 2, 3, 4 processes of the Carnot cycle. And let me just try to draw the the first heat input process. Okay. Now, in order to make all the drawing simple, let me assume that your working fluid is ideal gas. Okay. It doesn't really need to be that. Okay. So your working fluid of Carnot cycle can be ideal gas, can be water, can be anything. But at this moment, in order to make the whole drawing easier to understand, I'm gonna assume that that is an ideal gas. Now, for the ideal gas, we know that PV should be equals to RmRT, right? Then, how can you draw the isothermal process of an ideal gas where temperature is constant? So from this equation, temperature is constant, then what I can see is PV should be constant, or P should be proportional to 1 over V. So that is for temperature is constant. But now, from pretty high temperature and pressure, we have PV diagram, inversely proportional to V. So now, let's from 1 to 2. Okay. Then how about isentropy process? So what is the equation that you have to use to express the isentropic process of an ideal gas? To remember it. Now let me write it down. Do you remember this equation? Okay. So that equation is ideal gas and isentropic process. What it means is that during the isentropic process, we should satisfy P proportional to 1 over B powered by K. Here, K is always greater than 1 because K is specific heat ratio. So Cp is always bigger than Cv. So K should be always bigger than 1. Then the slope of this curve should be steeper than the isothermal curve. Now we can draw this way, 2, 2, 3. Okay. So then that is 1 over V proportional to, that is proportional to 1 over V powered by K. And from 3 to 4, that is kind of same as is, again, that is 1 over V proportional to, and from 4 to 1, we have steeper curve, that is again isentropic compression process, or 1 over V K proportion. Okay. Now, again, we learned from PV diagram that the whatever area underneath of the curve in the PV diagram is about work. So now, from 2 to 3, we have that much of work. From 1 to 2, that also gives us that much of work. Okay, so remember, for the Carnot cycle process, during the isothermal heat input process 1 to 2, still it must have certain expansion such that it does invert work process. And obviously, at the later part, then isentropic expansion work should be also the work process, that is process 2 to 3. Now, from 3 to 4, we also have the work, okay, that's needed by the counter cycle. And also from 4 to 1, that is also we need certain work in order to have the isothermal rejection and compression process. So for all 4 processes are involved in certain type of work, either expansion or compression. And now net work out, right, is the difference between the entire expansion work processes which are involved in 1 to 2, 2 to 3, minus the amount of compression work that the counter cycle needs that are involved in process 3 to 4 and 4 to 1. And now the difference is, again, the area around closed loop in PV diagram. So the area is also W net. Okay. So either you draw your counter cycle or any type of closed loop cycle in TS diagram or PV diagram, the area made by that closed loop of your cycle gives you the graphical representation of net workout. You have to remember that. Okay, now, then let's think about the performance analysis of the counter cycle. Okay, as I emphasized in a previous lecture, when you talk about the performance analysis, we basically have to think about 2 calculations. One is how we can get the net work out from the cycle, okay, particularly for heat engines. So because that is why we need to run the heat engines. So now, when you try to use a counter cycle for heat engines, then we must have that much of work, okay? And now, so that's the first thing we have to think about. And the second thing we have to always, analyze is what it would be thermal efficiency. So what is the thermal efficiency of the counter cycle, right? Let me tackle this net workout first. We already tried to derive these equations because from the first law of thermodynamics, no matter what cycle we are talking about, net work output can be expressed in terms of the difference between heat in and heat out. Okay? Now, from the equations that we tried to derive in earlier, now we can write it as area of the rectangle in TS diagram, which is, so as far as you know the temperatures, TL and TH, and the entropy, then you can calculate the net work output. Now, how can you calculate the thermal efficiency? Do you remember the definition of thermal efficiency of a heat engine? Let me write it down. So thermal efficiency of a heat engine can be written as 1 minus Q L out divided by Q in. Okay? So we know that Q out is TL S2 minus S1 divided by Q in TH S2 minus S1. And these 2 common terms are gone. So the thermal efficiency of the counter cycle can be expressed in terms of 1 minus TL over TH. So as far as you know the temperature, the top and the bottom, you can calculate the efficiency of the counter cycle. Now, that is a really, really important equation because, as I said earlier, the counter cycle is the most ideal cycle. What it means is that nothing, in the whole world, so no cycle can beat the kind of counter cycle, particularly in terms of efficiency. Okay? So let me write it down. Please write in your lecture note. I also, I wrote down in my lecture note that it's going to be uploaded to Canvas. So no heat engine can have a better efficiency than the Carnot cycle or Carnot heat engine. Okay. And the maximum thermal efficiency you can ever achieve is this. So that is the maximum efficiency you can achieve as far as you go for a cycle. Many times, in order to distinguish that Carnot cycle efficiency from any other cycle efficiencies, we define that as Carnot efficiency. And instead of eta sub th, we use eta c to present c as Carnot, or because everything is so reversible, we use eta r e b. Because again, the Carnot cycle is composed of entirely reversible processes.
Let's think of two, the reservoirs. One is heat source reservoir, whose temperature is at 1000 Kelvin. And there's another reservoir that is, heat sink at T L at 300 Kelvin. Now, we are going to try to, let's say, design a heat engine that runs, between these two heat reservoirs. Then now, what is the maximum efficiency that we can ever achieve? In order to calculate that, we have to use the thermal efficiency of the Carnot cycle, okay, which can be written as 1 minus TL over TH. So from the given value at TL at 300 Kelvin and TH at 1000 Kelvin, the Carnot efficiency gives us the value at 70%. Okay, so no matter what heat engine you can design, the efficiency, the maximum efficiency is 70%. Now let's assume that there is one heat engine whose efficiency is at 45%. Then this heat engine efficiency is smaller than the Carnot efficiency. First of all, that is possible to make. Okay, and why do we have a lower efficiency than the Carnot efficiency? Because this engine has a lot of irreversibilities. Okay, so I don't know exactly what kind of irreversibilities are there, but there are certain processes should be irreversible. Now, let's think about another heat engine. Okay, and in that case, this heat engine, let's say that is efficiency of 80%. Now, can you make this heat engine? The answer is no, that is not possible. Why? Because, as claimed, this thermal efficiency is greater than the thermal efficiency of the Carnot cycle, and this cannot happen because there should be no heat engine that exceeds the Carnot efficiency.